All right, so welcome to the lecture. So I'm going to start with a quick review of what we did last time. So if you remember, we had defined the Kelvin scale by using the idea of an ideal gas thermometer, and we talked about linear expansion of solid materials. And so I'll just have a quick review of both of those things before we move on and talk about some applications of thermal expansion. So we said that the Kelvin scale could be defined by using an ideal gas in a constant volume and measuring the pressure of that ideal gas. And we define the Kelvin temperature to be something that's proportional to the pressure that you would measure for this ideal gas. And in order to give a precise number to temperature, then what we said was that we're going to define this constant or calibrate the thermometer by saying that if you were to place that thermometer into water at the triple point, so there's this very specific temperature and pressure where ice, water, and steam can all coexist in equilibrium. And if you have your thermometer at that point, then we define that temperature to be 273.16 Kelvin. And then if you want to figure out or assign a temperature to any other situation, then you just place your thermometer in that situation, read the pressure off the gauge, and then, for example, if it's twice as much pressure as when you're at water at the triple point, then you say the temperature is 2 times the 273.16, okay, and so forth. So once you've done that one calibration, then you could figure out any other temperature based on the pressure. And once we have the Kelvin scale defined in that way, then the Celsius scale is just defined to be the temperature in Kelvin minus 273.15. And as I mentioned last time, the reason why we choose this number 273.16 is that with that choice, the difference in temperature between freezing water and boiling water at ordinary pressures is going to be about 100 Kelvin, as we're used to. So the temperature difference is in Kelvin is the same as the temperature difference in the Celsius scale. Okay, so then we talked about thermal expansion. And we said that if you have a material, could be a rectangular object, could be a spherical object, or an object of any other shape, and you look at any linear dimension of that object. So this formula applies to the distance between any 2 points that you choose. It could be the radius of a sphere, the length of the brick, the height of the brick, the width of the brick. Any of those linear dimensions, this formula will apply to tell you how that particular distance that you're looking at changes if you have a change in temperature. And so what we can say is that as long as we're talking about small changes in length, delta L over L is small, then that change in length is going to be directly proportional to the change in temperature. Okay. Furthermore, if you have an object which is larger, then the change in length is going to be larger for that larger object. So the change in length is also proportional to the original length of the object. In a minute, I'm going to have you remember and think about why that would be. And then finally, the change in length, given objects of the same initial size and the same change in temperature, some of them will still expand more than others. And that has to do with the basic property of the material that your object is made of. And so this coefficient alpha, it will be something that you can just look up for the particular material that you're interested in. So for copper, there's some value of alpha. For iron, there's some value of alpha. And so you would just look that up. Okay. So just as a quick thought question here, maybe pause the video and take a minute to think about the following. Why is it that the change in length of an object is proportional to its initial length, L? Okay, so if I have, say, a steel rod, and then I have another steel rod which is twice as long, how do we know that the expansion of the second rod is going to be twice as much as the expansion of the first rod if we increase the temperature? So pause the video, take a minute to think about that. Okay, so hopefully you've thought about it. The reason, we can give a couple of reasons really. So a basic underlying reason is that the expansion of this rod is really something that's happening at the molecular level. I'm going to say why that is in the next slide. But we can think of the molecules of the rod as on average getting further apart as we heat up the system. And so if we think about now our steel rod that's twice as long, and we look at the left half of that steel rod, well, every part of it is expanding, and every part is expanding kind of based on this formula. And so if we have the rod that's twice as long, the left half is going to expand just the same amount as the rod that was half as long. Okay, so we have this rod, it expands. Now we have the longer rod. The left half is going to expand just as much as the first rod, but the right half is also going to expand just as much as the first rod. Okay, because the expansion of some part of the rod on the left here, it doesn't care whether there's some other part attached to it. It's just happening locally. So it will behave just, the left half of your longer rod is going to behave in just the same way as the shorter rod. Okay, so that is why if you have a longer object that's twice as long, it's going to expand twice as much. The left half expands a certain amount. The right half expands the same amount. The total expansion is the sum of those two. So here's a little digression to understand why it is that when we actually heat something up, it tends to expand. So what I've drawn here in the first, well, I guess it's the second picture. This is a picture of two atoms in a solid. Same thing applies if there's some molecules. Let's just say we have a simple solid, maybe it's copper. So we have two nearby atoms, and so the starting point is to realize that there's actually some preferred distance. There's some least energy configuration of those two atoms, which would have a distance, what I'm calling R0. And so the way to think about this is that, let's say I just had two positive charges. Well, we know that they would actually repel each other, and the least energy configuration would be where those are infinitely far apart. If I have a positive and a negative charge, then they're going to attract each other, and the least energy configuration is going to be where those are very close together. But if I have two atoms in a solid, then those are usually neutral molecules. And with the neutral molecules, what happens is that they're going to attract each other at large distances, but repel each other at short distances. So let me try to explain why that would be. So actually, let's first think about something like a water molecule, where you have an oxygen and a couple of hydrogens. And in a molecule like that, you have some uneven distribution of charge. The net charge is 0, but you tend to have more positive charge on one side and more negative charge on the other side. And so if you have two water molecules, what will happen if they start far apart is that they'll tend to arrange themselves so that the positive charges in one molecule are closer to the negative charges in the other molecule. So they might rotate, and then kind of like if you have two magnets, they'll rotate around and then they'll attract each other. Same thing with neutral molecules. The charges in those molecules will kind of arrange themselves so that the positives here are facing the negatives here, and then they'll tend to attract each other. So that's why with neutral molecules, then you'll always tend to get some attraction at long distances, because the charges can rearrange so that the positives here are closer to the negatives here, or the other way around. Okay. But once they get too close together, so let's imagine trying to put these molecules right on top of each other, well, then those two positive charges are going to end up with a very, very large potential energy. So if I try to put the the two nuclei of these atoms right on top of each other, that will cost an infinite amount of energy because you have this Coulomb potential that goes to infinity as you place two positive charges on top of each other. Okay, so even though there's an attraction at long distances, there's going to be this repulsion that eventually happens if the molecules or the atoms get too close to one another. So in summary, there's some particular distance where you have the least possible energy. And if I go further out than that, it costs me some energy. If I go closer to that, closer than that, it costs me some energy. So I have to add in extra energy in order to get them either closer or further than that preferred distance. Okay. So if you have your solid and you chill it down to close to absolute zero, 0 Kelvin, then all of your molecules, you're removing energy, you're removing energy, you're removing energy, all of your molecules are going to try to be as close as they can to that ideal distance. Okay. And now let's think about what happens as you add energy to the solid. So as I heat it up, maybe I have collisions with outside air molecules, or some radiation is coming in and colliding or being absorbed by your molecules in the solid. So we're adding energy to that system. And now what happens is that energy you can think of as partly going to kinetic energy. So now these molecules can move around. And part of the time, that energy is going into potential energy. So the molecules can move around, but also they can get a little bit closer than the preferred distance, and they could get a little bit further away than the preferred distance. And so what you'll have are these random motions of molecules where they're now moving around. Sometimes they're closer to each other than R0, and sometimes they're further apart. And so that's kind of indicated in the second picture here, showing the possible configurations of the two molecules. Okay. But one thing you'll notice, now let's actually look at the detailed form of this potential energy graph. It slopes to infinity very sharply here, and then it's a more gradual increase to the constant value of potential energy that you'd have if the molecules are infinitely far apart. And so if I have a certain amount of energy, let's say I add a certain amount of energy, so now I can be at this energy here. So then the molecule can vibrate all the way from here out to here. It could explore all of these possible configurations. But you'll notice that there's a larger space of possibilities when the radius is greater than R0 compared to when the radius is smaller than R0. Okay, so what that means is that as the molecule is vibrating, sometimes it'll be closer than R0 to the nearby molecule. Sometimes it'll be further apart, but actually more often it's going to be further apart, just because there's just more configurations, more possible distances that it could be at when it has that excess energy. And so the vibration is like it comes a little bit closer, and then it goes quite a bit further apart, and a little bit closer and quite a bit further apart. And so this is happening randomly with all your molecules in the solid. And so in the end, the point is that on average, two molecules that are randomly moving around and vibrating, they tend to be further apart than the minimum energy distance, and on average. And so that means that on average, your solid is going to get larger because the average distance from between the molecules is going to be slightly larger than R0. Okay, so that's the microscopic explanation. Now, most of the time in this class, we're not going to think about the microscopics. We just mostly care about this macroscopic picture and understanding what are the effects on the macroscopic dimensions of heating up a solid. Okay, so this is this formula with delta L being equal to alpha L0 delta T. That'll be the main thing that we're going to make use of. Okay. So in many situations, you don't just have one material, you have multiple materials. So if you're building a structure, oftentimes you have maybe copper for part of it, or steel for part of it, or concrete for part of it. And these materials are attached to one another. And so it turns out to be very important to think about the kind of relative thermal expansion of various materials that are in contact. So in this question that I'm going to have you think about, you have a steel ball and it's slightly larger in diameter than the diameter of a hole in a copper plate. So this is maybe not obvious why we would care about this, but in the next question, actually, I have an application where you'll see that this is something like a real world situation in a car engine. Okay, but for now, the point is that we have this ball, we have this hole, and the ball doesn't quite fit into the hole. And what we notice if we look up in the table of expansion coefficients, we notice that the alpha for copper that appears in this equation is different than the alpha for steel. It's actually bigger than the alpha for steel. And so what we want to know is there some situation where this ball, the steel ball, will actually fit through the hole? Will it fall through the hole if we heat the system, if we cool the system? Will either of those things work or neither of them? So think about that. Pause the video, come up with your answer. If you want, also think about when you heat it up, does it get larger or smaller? And think about why that would be. Okay, so pause the video and we'll come back and talk about that. Okay, so let's understand how to think about this. The fact that alpha for copper is larger than alpha for steel, what it means is that when you heat up the copper, it's going to have a larger percentage of expansion than the steel. If you cool down the copper, it's going to have a larger percentage contraction than the steel. Okay, so now we can think of what would happen in this situation with the steel ball and the copper plate. If we heat up the steel ball and the copper plate together, then both of them are going to expand. But because alpha for copper is larger, the copper is going to have a larger percentage expansion. And so we could imagine that after a while, when you're heating these up and heating these up more, then eventually the hole in the copper plate is going to be large enough so that the steel ball can fall through. Okay, so that actually assumes that the hole in the copper plate is going to expand based on this formula. I should quickly review why that would be. Okay, so a number of ways to think about this. One of them is just that this formula applies to any linear dimension of an object. You can just pick any 2 points on an object, you look at the thermal expansion, and this formula tells you how much that length is going to change as you increase the temperature. Okay, so it could be the 2 points at the opposite end of a hole. Those are 2 points on your copper plate, and as you heat things up, then the change in length between those 2 points, it is governed by this formula, just like the 2 points at either end of the ball. Okay. Now, a way to understand that is to realize that the expansion is something that, again, it just happens locally at the level of the molecules. The textbook has a really nice explanation. So let's think about two copper plates. One of them has a hole in it, and the other one just has drawn on the top of the copper plate a circle which is the same size as the hole. And now we're going to heat up both of those plates. Okay. And so the point is that the copper molecules outside of the hole, away from the hole, or outside of this circle that we've drawn on it, they're just going to expand as they would. They don't really know about whether there's a hole in the plate or whether there's just a circle drawn on the plate. Those copper molecules far away from the hole or outside of that circle, they are just going to behave. All they know is they're being heated up, they're going to expand, and so they're going to behave in exactly the same way in both cases. Okay. And so in both cases, the copper on the outside of the hole, since we know it's going to behave in the same way, it's clear that in both cases, then that hole is going to get, well, it's clear in the case with the hole, it's going to get bigger, because in the case with the circle definitely gets bigger as the plate expands. The whole plate expands, the circle is going to expand. And so because the copper on the outside of the hole behaves just like the copper on the outside of the circle, then that will also expand. Okay, so that was probably too long-winded, but hopefully you got the point there. So now we're pretty convinced that the copper is going to expand more when we heat it, and that the steel ball will fall through. If we chill it down, then the copper is going to contract more than the steel ball, and so that's not going to work. Let me do a demo. So just to really convince you that this is what's going to happen, I actually went into our classroom and recorded the real experiment where we had a copper plate and a steel ball. So I'm going to share the video here. You can have a look at that. Here we go. Okay, so that should be coming on. All right, we're back here. Okay, so it was nice to see that the experiment actually showed what we predicted. It showed that as we heated the system up, then the steel ball was able to fit through, and we understood that as being because the copper plate had a greater percentage expansion than the steel ball. So the next thing we want to think about is the quantitative version of that. So we want to think about in a specific situation where we know that, say, the radius of the ball is larger than the radius of the hole by a certain amount, say 0.001 centimeters. Maybe that's at room temperature. We would like to be able to predict how much do we have to increase the temperature of the steel ball and the copper plate so that the steel ball will fall through. Okay, so we understood that if we increased it enough and we applied the formula, that the copper would expand more. But do we have to increase it by 10 degrees Celsius or 100 degrees Celsius or 1,000 degrees Celsius? If it's too much, then the steel or the copper would melt. So we'd like to be able to quantitatively make this prediction. And so that's what this next question is going to be about. Okay, so I want you to take a few minutes, definitely pause the video here, and think about a strategy for solving this question. So the only formulas that you're going to need will be this one that we've talked about with the thermal expansion, but we have to take into account the fact that the coefficient of thermal expansion, alpha, is different for steel as compared with copper. Okay. So pause the video and then we'll come back, and I'm going to tell you about a strategy for solving this problem that applies to many of our problems in Physics 157, and we'll see how we would set this up. And you'll be doing a very similar problem on tutorial next week, so I won't go through all of it. Okay. So let's pause it. I'm going to get my camera ready to show you that derivation. All right. So let's think about this question. And I want to start by talking about a general problem-solving strategy that you're going to use for many of the more complicated problems in this class. So the thing that makes this a little bit more complicated than, say, the bridge problem we had last time is that there are two different parts of our system. In some problems, there might be 3 different parts or 4 different parts. And so if you have a problem like this, one way to approach it is to think about, first, what happens to the individual parts of your system. Based on what you're told in the question, think about what happens to the individual parts. Use whatever quantitative knowledge, whatever formulas apply to those individual parts that are relevant to the question, and just make a list of things that will happen. So that's sort of step 1. Step 2 would be to understand, based on the description of the question, how are quantities related, how are quantities that apply to the individual parts related to each other? What needs to be true in the specific situation that you're being asked about? Okay. And so for this question, I'm going to think about let's read the question. Maybe actually a important initial starting point would just be to, understand what is it that you're being asked for. Okay. And so we're being asked, to what temperature must we heat the system before the ball falls through? Okay. And so it's often convenient to say, since there's going to be some unknown variable that we're trying to find in the end, I'm just going to give that a name. So for this problem, I'm going to actually say delta T is the thing we're trying to find. So I could have said the final temperature is the thing we're trying to find. It'll be a little bit more convenient for me to say I want to first find how much temperature change do I need, because that's the thing that will come into the formulas. And so I'll let delta T be the required change in temperature. Okay. So now I'm going to think about step one here, which is what happens to each part of the system. Okay, so I'm going to do that first because it's very simple. So here we're talking about thermal expansion, and the same thing applies for both parts. So we can say that the steel ball expands an amount delta L given by our thermal expansion formula. So delta L equals alpha steel times L0 steel times delta T. And so we know everything in that equation except for delta T. If we knew delta T, that would tell us delta L. And similarly, we could say that the hole in the copper, okay, I should actually say this is the radius, and the hole radius in the copper expands by, so that was delta L steel, delta L copper, and that's given by delta L copper equals alpha copper times L0 copper times delta T. Same delta T for both. So now we've understood what happens to the individual parts. Now we have to ask ourselves, what needs to be true about those individual changes in length in order for the conditions of the problem to be satisfied? So what we have is a steel ball that's originally 0.001 centimeters bigger than the hole in the copper plate. And so both of those things are going to change: the size of the steel ball, the size of the hole in the copper plate. What we want is for the hole in the plate to expand enough so that the ball can fall through. And so what we need is that the change in the length of the copper plate minus the change in the length of the steel has to be equal to or bigger than 0.001 centimeters. Okay, so 0.001 centimeters is the amount by which the hole is initially smaller. And so what we need is, after all the expansion happens, we need that the copper plate has to expand more than the steel ball, and the difference has to be 0.001 centimeters. And so now we're in good shape. The rest is math. So we're going to see this in detail in next week's tutorial. Basically now all we want to do is plug this equation. So we have an equation for what delta L is. We have this equation for what delta L steel is. We're going to substitute in those two equations, and then we end up with a final equation where the only unknown is delta T. And so we'll isolate for delta T and then solve. So if you want, you could try to complete that question, but you're going, as I mentioned, you're going to see it next week, and similar questions on the homework next week. Okay. So just to finish here, I'll mention a question. I'll kind of tell you why this is relevant for some situations. So I'm going to mention a question that we'll do at the very beginning of Monday's class, and it's about an internal combustion engine in a car, something that we'll talk about later on in the course. So the thing to understand is that you have a cylinder of metal, and you have a piston, which is also so you have the cylinder is a hollow cylinder of metal, and then you have sort of a solid cylinder of metal, and that moves up and down in the cylinder. So the piston moves up and down in the cylinder. When you ignite fuel inside, that's what forces the piston down, and then that comes back up. And so this is what's happening inside an engine. Okay. But oftentimes the material of the piston is not the same as the material of the cylinder. And so you might have an aluminum piston. Maybe you want maybe you want a metal with a low density, and you build the piston out of aluminum, or maybe it's easier depending on how easy it is to manufacture these different shaped parts. You might choose one or versus the other. Sometimes cost is a factor. So for many reasons, you might end up with one metal that's different than the other metal. And so we have to think about how to design this. And so you basically want the piston to fit just perfectly inside the cylinder, but your engine has to operate not just at a single temperature, but at a range of temperatures. That might be between 0 degrees Celsius when you just turn your car on a cold day, up to something like 120 degrees Celsius. And so you have to think about, well, how are these things going to expand or contract relative to one another? Okay. And so I'll leave you with that. You can think about it over the weekend. We'll see it again on Monday, and then we'll talk about the answer.